Welcome back. In this video we're going to discuss surface integrals of scalar functions, and the main goal of the video is to derive the formula for how we evaluate surface integrals of scalar functions. And the main steps for setting up any definite integral, as we've seen in our work in Calculus 1, 2, now 3, is to chop up the region you're integrating over into a large number of pieces. For each piece, plug it into the scalar function f and then multiply it by the size of the piece under consideration. And as we've seen in our work, that could represent a length of an interval. For a line integral, that represented an arc length. For double integrals, it represented the area of the region we were integrating over. For triple integrals, it represented the volume of the region. So that size could mean different things in different contexts, as we've seen. Take that result, add them up for all the pieces over the region, and then take the limit as the size of the pieces shrink to 0. Or stated differently, the number of pieces increases to infinity. Alright, so that's how we write down a definite integral in terms of Riemann sums and the limit of Riemann sums. For surface integrals, it's going to mean the following. And notice here we're talking about the surface integral of a 3-variable function. If we're talking about a surface in 3 space, we've got to have a function of 3 variables, and there's the limit definition for that surface integral. And again, things to key on in here is that the delta S sub k over here is going to stand for the size of the kth piece of the surface, which we're going to cut up, and it's going to measure the surface area. Therefore, the size of the surface is going to mean surface area. And as we've seen in our previous work for double, triple integrals and line integrals, evaluating with the limit definition is not an easy task. So what we need to do is find a different approach. And like with line integrals, the idea is to pull the problem back via a parameterization. In this case, it's going to be to a region in the UV plane. All right, via the parameterization. For line integrals, we used a parameterization to pull the problem back to an interval. All right, and that gave us a scalar single integral. For surface integrals, it's going to turn out we're going to have a double integral. Alright, now continuing on, we'll get to that derivation. So we've got a little graphic here from the OpenStax textbook. So we've got our surface on the right hand side. Alright, and we're cutting it up into pieces using the parameterization. Alright, so we partition the u-axis and the v-axis, and that's going to determine a rectangular grid. And if we fix v and let u vary, then these lines get mapped over onto these corresponding trace curves on the surface. If we vice versa fixed u and let v vary, then we would see that these vertical lines would go over to these image trace curves on the surface. Right. And now what we're going to do is we're going to key in on one patch on the surface right there, S sub ij. Alright, again, we're partitioning the the u-axis, the horizontal axis, up into many pieces, and that is going to be the partition u sub j, or u sub I, and the v-axis is going to be the partition v sub j. Alright, and what we're going to key on is one piece there. Alright, and what we're going to focus in on is what happens to these 3 corners of this rectangle in the UV plane. They get mapped over to these 3 corners of that surface patch. Alright, and then let's label what those are by redrawing this down below here. Okay, so again, we're going to focus on that curved patch of surface. Alright, and then the 4 corners of that are coming from the 4 corners of the rectangle in the UV plane. But what we're going to do is we're going to focus on the lower 3. Alright, and what we're going to do is we want to, in the limit definition, we need to compute the area or the size of that patch. Right? That's the patch we're focusing on right there, S sub ij. Now, writing that out explicitly is a difficult task. What we're going to do is approximate it. And the way we're going to do that is connect these 2 points. Alright, we're going to label these points. We're going to call this P sub 0. P1 is going to be the lower right corner, and then P2 will be the upper corner there. We're going to connect those points by vectors, and then instead of finding the surface area of that curved patch, we're going to look at the corresponding parallelogram that we're going to determine using these two vectors. The vectors that connect P sub 0 to P1 and the vectors that connects P0 to P2. And we're going to say that the area of the surface area of the curved patch will be approximately equal to the area of the parallelogram determined by these vectors. All right, hopefully it's clear that those surface areas will be in fact close to one another. All right, now let's write a little more detail about what these points are. The point P sub 0, remember, was coming from, it was the image under this parameterization of that rectangle. Well, the lower left corner is u sub I v sub j. So P sub 0 we can actually write down in terms of the parameterization, it's r of u sub I comma v sub j. P1 is the image of the lower right corner, and its coordinates are u sub I plus delta u, one step to the right, and then u v sub j. So the coordinates at this point we could write is the image of the point u sub I plus delta u, comma v sub j. All right, the point P2 is the image of the point u sub I comma v sub j plus delta v. So under the parameterization, it's the image of that point there. All right, and now what we want to do is just write down what those vectors are in terms of the parameterization r and those image points, and then where we'll find the area of this rectangle. Let me just try to redraw, or that parallelogram. Try to redraw this here. All right, there's the parallelogram determined by those vectors. Now, from our previous work this semester, we know how to connect two vectors together. So if we look at P0 to P1, we know that as vectors we do the vector difference P sub 1 minus P sub 0. All right, let's write one of these out on this page, and then we'll continue on. I have it typed on the next page. So putting that in terms of what these vectors actually are under the parameterization, it's going to be P1, which is r of u sub I plus delta u, comma v sub j minus, that's a kind of vector, minus r of u sub I comma v sub j. Okay, and likewise we would have from P0 to P2, this time we're fixing u at u sub I. We're going to let v vary. It's going to vary from v sub j plus delta v minus the same starting point. Alright, so now what we want to do is use the result that we know that the area of this parallelogram will equal the length of the cross product of these two vectors. Alright, so we saw that in our previous work this semester, that the length of the cross product gives you the area of the parallelogram determined by those vectors that you're taking the cross product of. Okay, so continuing on then, again, the idea is that if we thought about superimposing in here the parallelogram, that the area of that parallelogram will be very close to the area of the surface patch, the curved patch. Alright, so just on the next page I've just wrote down what those vectors are that we had before. Now again, what we're saying here, and the key thing is that the surface area that we're looking for is going to be approximately equal to the length of that cross product. Now what we need to do next is get a better expression for that, because what we want to do is let delta v and delta u each approach 0, and we can't get a very good expression using those difference vectors because they'll both approach 0. Alright, so let's see how we're going to be able to rewrite that. Alright, it's going to turn out that we're going to rewrite that in terms of the partial derivatives. So we're going to kind of pause on that derivation for a second to go through a discussion of how we can rewrite a difference in terms of a partial derivative. Alright, so here's the definition of the partial derivative of a two-variable function. And it's very similar to the definition of the limit definition in terms of the difference quotient for partial derivatives of scalar functions. The difference is in here that these are vectors. All right, we're not getting numbers here. These partial derivatives are vectors. So notice here what's changing is for the For the u partial derivative, we're letting u vary, fixing v, and vice versa for the v partial derivative, we're letting v vary, fixing u. All right, now for this, what we want to do is consider a fixed delta u. So let delta u be fixed, and we're thinking about it as, you know, a small change. All right, so delta u is a small number, but we're going to say it's a fixed number. So when we do that, we can no longer write down limit as delta u is approaching 0 because we're not letting it approach 0. So we cannot write equals there. We have to replace the equals by approximately equal to, and we drop the limit sign, and then just copy everything else down. So write the difference quotient out. All right, and notice we don't have limit there, and we're thinking about delta u being fixed. All right, now what we see is in the numerator we have a difference of two vectors. And notice how up in these vectors P0 to P1 we have a difference of two vectors as well. All right, so we want to get just the difference vector up in the numerator by itself. So what we're going to do is clear the fraction by multiplying by delta u on both sides. That will give us just the difference, and then I'm just going to rewrite this on the next line. So I'm going to rewrite this by flip-flopping the sides. I'm going to put the right side on the left now. So we have the difference r of u plus delta u comma v minus r of u v will be approximately equal to the partial derivative vector times delta u. Okay, so we can replace that difference, as long as delta u is reasonably small, by the difference of those two vectors by the partial derivative vector times delta u. Okay, and using a similar analysis that we won't do with the partial derivative with respect to v, we would have that if we fix u and let v vary, that difference vector, the difference of those vectors, can be approximated by the partial derivative of r with respect to v times delta v here. And now what we're going to do is just substitute in from above what we had. All right, now what did we have before there? We had as the vector P0 to P1 r of u sub I plus delta u comma v sub j minus little r of u sub I v sub j. So this will be approximately, not equal to, just approximately equal to the partial derivative of r with respect to u at the point u sub I v sub j times delta u. And likewise P0 to P2, that vector connecting those was fixing u this time at u sub I, letting v vary. And we can then approximate this by the partial derivative of r. Again, it's a vector. The partial derivative vector with respect to v at the point we're focusing on, the lower right corner, and then times delta v. All right, now that's going to help us to get an expression that we're going to be able to then work with in the limit definition. Okay, so continuing on here. Again, what we're saying here is that we're going to look at, in the figure, a couple of vectors that are close to but not curved in here, and those vectors are going to be the partial derivative of r with respect to u times delta u, and the partial derivative vector of r with respect to v times delta v. All right, and then we just need to write the cross product down and see how that's going to help us in the limit definition. All right, now in this video I don't have enough time to complete that, so we'll do that in the next part.